Alright, so I'm gone today. My daughter is sick today, so I'm home with her. Um, Today we are doing the lesson 4.6, the natural base E. You can see the homework assignment there, page 278, numbers 13 through 22, 25, and 30 through 36. So today we're going to go over 4.6. After that, you should have some work time on the homework, any chapter 4 homework. Hopefully you can get everything done for today. And then the review, which I guess I'll write that on right now. Okay, there we go. Page 298, and then numbers 1 through 40. That covers the first 6 sections. Since I'm gone today, originally the plan was we were going to do 4.6, then do homework time and review time, and then do the test tomorrow. So what we're going to do tomorrow instead is we're going to begin chapter 5, but also I'll take any questions on the 4.6 lesson or any other chapter 4 stuff. We're not going to spend a ton of time on that tomorrow, but I'll take questions, and then we'll do the test on Thursday, and we'll also do the second chapter 5 section on Thursday as well. That's what I'm thinking at least right now, so let's get started. So the number E, it's kind of weird to hear it called a number, but E is a number. It is an irrational number, and what that means is that it's a decimal value that goes on forever without repetition. Okay, E is approximately equal to 2.7182 81828, and it looks like it's repeating, but then if you keep going, 4590 ... Okay. And so that's approximately the value. It's called Euler's number, and Euler is spelled with an E. He's a mathematician who happened upon this number. We use it for, used for real-world situations when continuous growth or decay is desired. Okay. So before we talked about types of growth that are based off a rate, yesterday we talked about growth and decay, or really we only talked about growth yesterday, of compounded, monthly or quarterly, a few times a year. This is going to be continuous growth. So that means it's growing at every moment, every second, every half second, right? So that's what continuous means, at all times growing. And this is more appropriate for real-world situations like population or the decay rate of certain elements that scientists can use to, like carbon dating. You might have heard of that before. They can use carbon dating to tell the age of a bone or something. And that's because the carbon decays at a certain rate, and they use the natural base E to help calculate that. All right. Alright, we're starting off with a joke. Noah is asking, what are you studying? Taylor says, E. Noah, natural logarithms? Taylor, no. I mean E. There's a wasp on your leg. Ooh, that is pretty scary, rat wasp. Okay. But yes, we are learning E, and it does have this connection with natural logarithms. Okay. We'll talk about that as we go. But first off, let's look at graphing this function e to the x power. So we have a table, and if you look on your calculator, you'll see a button that has an E on it. Now you might have, well, it doesn't have to be a graphing calculator. Scientific calculators have the E button as well. Most of the times you have to use the second feature. So like on this graphing calculator, I'd press second, and then if you see the LN button, the second option is E. And oftentimes it'll force you to raise it to a power because we often raise E to a power. So for example, E to the negative second power, that'll be the first thing in our table. Press enter, and I get about, let's just round to 2 decimal places for the graphing purposes, so that'd be 0.14. Okay. And since I already entered these in, I'm just going to start giving them to you. So 0.37 to the 0 power is still just 1 like it usually is. To the first power is 2.72. Second power is 7.39. And third power 20.09. Alright, so let's graph this. Make a couple marks going both ways. Okay, so negative 2.14, that'd be pretty low. Negative 1.37, a little higher. 0, 1, 1, 2.72, so 1, 2, 3, somewhere about there. 3 or 2 and up 7.39, 3, somewhere about there. And 3, 20.09. I don't think we're going to be able to hit that. 9, 10, 11, 12, 13, 14. So it'd be maybe up there somewhere. Doesn't cross the x-axis. There we go. Kind of looks like a fairly standard exponential curve. So this is a growth because it's going up. Well, from left to right, it's going up. That's basically how you can decide if it's growth or decay. Domain, it's going to the left forever and the right forever. That's all real numbers. But the range, it goes up forever. It does not go down forever. The lowest it can be, well, it doesn't even touch 0 technically. So it's all the y values that are greater than 0. There's that, remember that word, we had it in a joke before called an asymptote. It's an imaginary line that you can't cross. So that's the x-axis right there. All right. Let's take a look at another graph that's similar to this last one. So it's e to the x plus 2. So you could always punch this in your calculator, or since we just graphed e to the x, well, e to the x plus 2 means you add 2 to all those values. So we have 2.14 and 2.37 and 3 and 4.72, 9.39, and 22.09. So it's pretty easy. We're just not going to bother with negative 3. It's going to be 2 point something. Okay. So what this actually does when you add 2 like that, that's too close together. What it does is it shifts a graph up 2. And if you recall, we've seen graphs like that before, like with parabolas and stuff. Plus 2 makes it go up 2. So anyway, that asymptote, that horizontal red line that I drew, dotted line that I drew on the last one, is going to get shifted up 2 as well. I'm going to draw that in first. So, negative 2 up 2.14, so just above that red line. And then negative 1, 2.37, a little higher. 0, 3. 1, 4.72. 2, 9.39. About there, and I'm not going to be able to fit the 22 in there, so I'll just stop there. Okay, so something like that. This is still growth, since going from left to right, the graph is going up. The domain is all real numbers. The range, now it's going to be a little different this time, so it's all y values that are greater than 2, since it got shifted up 2. All right, so now that leads us to the natural logarithm, okay? Natural logarithm. It is the logarithm that uses base e. So it looks like this. It's ln. I usually use a cursive L because otherwise it might look like a 1. So you can think of this. This is just our way of writing log base e of x. It's called the natural logarithm because e is called the natural base. And that button is on the calculator. You don't have to write press second to get it. It's just ln, right? For this one, it's kind of to the left of the 4 there. So like the natural logarithm of 6. You know, what is that? 1.79. So yeah. Okay. Now the natural logarithm function, that would be f of x is equal to the natural logarithm of x. This is the inverse. So it's the inverse of the function with the base e. So it's the inverse of f of x equals e to the x. Because remember, exponential functions and logarithmic functions are inverses of each other, and it depends on what the base is. So these are both base e. Okay. Now, what would that look like if you were to sketch a graph? Lower that a little bit. Okay. So I'll graph the natural logarithm in red, and let's go the exponential function in blue. We already graphed the exponential function. It goes 0, 1, and it's got growth like so. Excuse me. All right. And remember how it gets reflected about that diagonal line when you're talking about inverse functions. So the easiest one will be right there, and then it's going to run alongside this and go like so. All right, so yep, this is the logarithm. This is our exponent function. Okay? And again, hopefully that's not too mind-blowing because we've seen exponential functions and logarithmic functions before. These look very similar to other ones that we've seen. All right, let's utilize another joke. Let's see. I don't know what this one is. Oh, this is that joke on the cover. All right, so the log says people have 10 fingers and 10 toes. It makes sense to use base 10. All right, and remember, if there's log and there's no number written down here, it's called the common logarithm because it's an unspoken base 10. So let's see. Then the natural logarithm's argument is natural e. I don't know. So it says a base of e, so naturally, you know, 10 fingers, 10 toes. So anyways, I guess the logarithms have their little arguments here on who's better. So, well, right now we're focusing on the natural base e. Okay, so remember, if a logarithm and an exponential function have the exact same base, there's some canceling properties that we can have. So like for part A, this is natural log and the base e, that cancels because they have the same base, and we're just left with negative 2t. Same thing as if it's written as an exponential function raised to a power of the natural log. Those cancel because they have the same base, and we're left with t minus 1. Now part C is a little different. You've got to rewrite it. So remember, we have to use some rules. If a number is going to be multiplied out in front of a logarithm, you can rewrite it as a power on the inside. So that would look like this. E to the power of natural log x to the 5th power. And now we can cancel out the e and the ln, and then we're just left with x to the 5th. So a little more work on that one. For part D, natural log and base e cancel. You're left with 3.2. For E, though, for part E, we have to raise that as a exponent, so that would be e to the natural log of x squared. Now we can cancel, and we're left with just x squared. And then here we have the natural log of base e. Those cancel, and we're left with x plus 4y. All right, now for where the base e really shines, okay, when we are using it for in the real world situations. So, interest compounded continuously. Whenever you see that word continuous, that's when we're going to use the base e. And we have this formula that we call A equals PERT, because it looks like it's P times e to the RT, and it looks like the word PERT. And if you know, PERT is like a shampoo or something, so it's PERT, not just for your hair anymore. That's the slogan we're going with. But remember, it's not that RT on PERT must be raised as an exponent. So anyway, so let's talk about all the different parts of this formula. So A is the final amount that you're going to end with. E is our base E, but it's just, yeah, the base E. It basically tells us that this is continuous growth or decay. So I'll say continuous G/D since I'm running out of space. So growth or decay. T is our time, and that could be in, any time. Minutes, seconds, years, whatever. P, the capital P, is the initial amount. So what you start with. And R is your rate, your growth or decay rate. Okay? If it's growth, then the R, notice that the R is in the exponent. So if it's growth, then that's a positive value. If it's decay, then it's a negative value. All right, so what is the total amount for an investment of $1,000 invested at 5% for 10 years, compounded continuously? Since it says that last thing, compounded continuously, that tells us to use the formula A equals PERT. So let's plug some values in. So A is equal to, our initial amount is 1,000, and then times E to the power of, R is 5%, that's 0.05, times 10 years. Okay. Let's use our calculator to help us out here. So that would be 1,000 times E, so get second ln, to the 0.05. Or some of you might need to use parentheses here. Here, I'll just show. So parentheses 0.05 times 10 in parentheses. And press enter. About 1648.72. So that's approximately $1,648.72. So this is not compounded like monthly or anything. Every single moment is being compounded. All right, let's take a look at another one. So we've got, what is the total amount of, for an investment of $100 invested at 3.5% for 8 years and compounded continuously. So same kind of idea, just different numbers. So 100 is our initial E because it's continuous. 3.5% is 0.035 times 8. All right. Go to our handy dandy calculator here. So 100 times E to the power of yeah, darn it, did it again. Parentheses 0.035 times 8 in parentheses. Enter. And $132.31. Okay. All right. So we've been talking about exponential growth with BASE. Now let's talk about a situation, real-world situations where we would have decay. So we call it a half-life. I think there might be a video game called Half-Life, but I don't know really what it's about. Maybe it's about this, but the half-life of a substance, it's the time it takes a substance to naturally decay to half of itself. Okay. So like if there are, 100 grams of this substance, it would naturally decay, and we want to, and this half-life is the time it would take for it to become 50 grams of that same stuff. Okay, this happens a lot with unstable, compounds and elements and stuff. I'm sure you might learn about this in chemistry class. This is a pretty big chemistry application. So anyway, N of T is our final amount, what we're going to end with. E, again, is that base of E. And this is telling us that this is continuous, right? And in this case, we're specifically talking about decay. So because this is half-life, it's always getting smaller, the amount of the substance. T is the time, and it can be in, whatever units. Depends on how fast this stuff decays. If it decays really slowly, you might talk about years. If it decays really quickly, you could talk about minutes or days. Okay, N sub 0 or N naught, sometimes is how we say it. It's N naught. That is the initial amount, how much you start with. And K is your decay rate or decay constant. It's already got a, notice in the formula, it already has a negative right in front of the K, so that K value is going to be given to us as a positive value, but the negative in the exponent is what makes it decay, what makes the values get smaller. All right. So let's take a look at this. A paleontologist uncovers a fossil of a saber-toothed cat in California. He analyzes the fossil and concludes that the specimen contains 15% of its original carbon-14. Carbon-14 has a half-life of 5,730 years. Use carbon-14 dating to determine the age of the fossil. So we're looking for T, the power of T. That's what we're looking for, is the age. All right, now before we can find the age, though, we have to find out what the constant decay rate is, that K value. So let's use the information that we're given here. So we know that the half-life is 5,730 years. So if you're going to so here, let's rewrite the formula. N of T is equal to N naught times E to the negative KT. So we're going to start off with, let's just say, 1 unit. One piece of carbon-14, one element. And then in 5,000, so then times E to the negative K, and the time would be 5,730 years. Over that amount of time, we have half of what we initially had, so that brings us to 1/2. Right? You could have plugged any number in here, and then whatever you plugged here, it should be half of it. It's just easiest to simplify it to the most basic one, which is 1 1/2. All right? So now let's calculate. Well, that 1 times, that really doesn't play a part, so we can ignore that. And I'm going to, okay, that's negative K times 5730. Now we want to solve for that K. Now, in order to get those exponents down, we have to do a logarithm to both sides. Now, this is actually kind of nice because the calculator has a natural logarithm on it, so we can do the natural logarithm of both sides. So natural logarithm of 1/2 equals the natural logarithm of E to the negative K times 5730. And the nice thing about that is, right here, the natural logarithm of the base E cancels. And then we just have the natural log of 1/2 equals negative K. And actually, you know what? I'm going to multiply all that together, so that would actually be negative 5,730 K. And to solve for K, we would divide by negative 5,730 on both sides. It cancels here, and K is approximately equal to, use our calculator here, so the natural logarithm of 1/2, or I'm just going to type in 0.5, divided by negative 5730, and that's, one of those things when it's got the E in there. Well, don't be afraid of that. Remember, that's scientific notation. So that just means that E to negative 4 means we move the decimal 4 times to the left. Okay? So that would be 0.000, so that would be 1, 2. So 1, 2, 3, 4. Yeah, that's right. And is it negative or is it positive? Okay, it's a positive value. Okay. So that's our K value. Okay. Now that's going to be good. Now we want to know the specimen contains 15% of its original carbon-14. And we want to know the age of this fossil. Now we want to solve for the K, or T, I mean. We have the K. 0.00012. Alright, therefore, we're going to do another version of this formula. We want to end with 15%. So if we start with 1, and then we have E negative 0.00012 times T, we're trying to solve for T. If we start off with 1 piece of carbon-14, then we're going to end up with 15% of that, so that'd be 0.15. Okay, that's going to be our final amount. Now again, you could have done anything. You could have done like 100, and then 15% of that is 15. But you're going to have to end up dividing by that 100 anyway, so Might as well just go to the most basic form. Again, since that 1 is just 1, we don't really have to worry about it. Now we're going to do the natural logarithm to both sides again. So at this point, it's pretty similar to what we did on that last set. So that I can fit it all in there, okay? The natural logarithm and e cancels. We're left with natural logarithm of 0.15. It's equal to negative 0.1 or 0.0012 t. Divide both sides by that negative 0.00012. And t is about equal to, let's see here. So we had the natural logarithm of 0.15 divided by negative 0.00012. Enter. And 15,809 years approximately. Alright. So that's how old this bone is, according to the carbon-14. Alright, so let's use the rest of this time well to get homework done and then get some practice with the review. You should have probably about maybe a little less than an hour to work. Okay, see you guys tomorrow.